4 degree. Okay? So the angle is very small. So usually if the angle is smaller than 5 degree, you can use that approximation. Tangent theta equals sine theta, you can use that approximation. If the angle is less than 5 degree. Okay, so you got this. You can put it here. You can solve the d first. Then d for the grating is just the lambda divided by sine the angle. The wavelength for the yellow light, so that's 589 nanometers times sine the angle. 2.40, right? Okay, so you will get then D is 1200 per thousand. 780 nanometers. Okay. Don't worry the number because nanometers, that's very small. It's just 12 micrometers. Okay, so once you got the D, so for another source, let's tell you for another source, produce that first peak is that X is 3.71 meters from that central peak. So just recall this formula. But this time, D is still this D. Sine the angle changed to the unknown wavelengths. Unknown wavelengths, I use the wavelengths. Okay, just use the theta 2, okay? Second angle, theta 2 equals the wavelengths. The wavelength is also unknown, 2, lambda 2. Because we need to determine it. But D is the same D, but the angle is changed. But to tell you that X is 3.71, so that angle, tangent of that angle, theta 2 equals 3.71 centimeter divided by the distance between the spring and the grating, that's 72 centimeters. Okay? So from this, you can calculate the angle of theta 2. Theta 2 is anti-tangent to this number. So the angle equals 2.95 degrees. Okay, you got that angle, then you can back to this formula. The angle is known, the distance, the D is known, so we can calculate lambda 2. So lambda 2 is just then D, this number, times the sine this angle, theta 2, 2.95 degree. Okay? So you find that wavelength is 658 nanometers. Okay? From the first sentence of the problem, from the yellow lights, we determine the D. The separation between the two states on the grating. So we got the D, then for the second part of that statement, so we can determine the wavelengths. Just again use that formula. So the second question asking you how many states per centimeter on that screen. Since you know the adjacent distance between the two states on that grating in this number, so they're asking you how many states per centimeter, just another reciprocal. Okay? So that one you can use another, that's just 1 over d. Reciprocal of that constant just give you the how many slits per unit length. Okay? In this case, it's just 1 over 1,000, 12,690 meters. Of course, you will get how many slits per nanometers, then you will convert to centimeters. This one is just nanometer, just times 10 to the minus 9 meters. Meters convert to centimeters, you times 2, we got centimeters times minus 7, okay? Okay, so you get the 782 per centimeter. Okay. So when you do problems, just to make sure you understand the question, what quantity they're asking you. You need to convert to some conversion sometimes. Any question about this point? Okay, so let's look at the last one. We're talking about the thin film. Thin film interference. Let's look at the problem for the 54. Okay. 54. So 54 talking about a thin oil slit floats on water. Give you the index of the oil, index of water. When the beam of white light strikes normally incident from air on that oil slit, only enhanced reflected colors are red and violet. From this information, we use the minimum thickness of that oil slit. Okay, so we need to use that condition for the constructive interference on that slit. I think we have over here. Unfortunately, that's not all it. Let's look at this. That's the condition for the constructive interference on that slit, same thing. But here, it's even more complicated. The oil slit is actually floating on a water surface. Basically, they have two interfaces. This is oil. The water is down here. This is air. Air, the index is 1. The oil, the index is 1.5. The water, 1.33. So the white light is incident normally. And the first interface will reflect from air to the oil. The air index is 1, oil index 1.5. So from low index to high index, we talk about here. So there is a pie shift. There's a pie shift. From low index reflected by the interface from the high index. So there is a pie shift here, reflected lights. Then the lights get into the oil, then reflected the second interface. The second interface between the oil and the water. This time you need to compare the index. index oil is 1.5, the index of water is 1.33, so 1.5 is bigger than 1.33. So still from high index to reflected to the interface of the high index material, low index materials. So the second reflection, no pi shape. Because the lights from the oil to the water, from high index to low index, so there is no pi shift. So this is just the opposite for the condition for the total internal reflection. Total internal reflection can occur when the lights coming from high index to low index. But here is pi shift is different. Only from low index to high index, reflector will get to the pi shift. Here from high index to low index, no pi shift. Okay? So no pi shift, the phase difference for those lights is just because of the path difference. So the path difference, if the thickness of the oil is T, the path difference apparently just 2 times T for the secondary reflected lights. The path difference just 2 times T because they go through here, then back to here, so they go to 2 times of the thickness of the oil. So that's the path difference compared with to that point. When you recall that formula, we know the path difference we can convert to phase difference. Just times 2 pi divided by lambda. But remember, lambda should be the lambda in that oil, because that light is traveling in that oil during that process. So you need to convert this to phase difference times 2 pi divided by the lambda, but the lambda should be in the oil. The lambda oil. Okay? That's the phase difference for the secondary reflected light. Then you need to compare the total phase difference. You need to compare with the first reflected lights. First reflected lights change the pi, so this one is minus pi. That's the total phase difference. And that's the total phase difference for the 2 reflected lights. Then get to that point in the air. So that phase difference should be integer multiple of the 2 pi. Then you will get the constructive interference. 2 pi times m. So this is a constructive condition. Okay? Okay, so next you need to solve the t. Because the problem tells you we need to solve the t. We have 2 different lambda. We have 2 different lights, red light and violet. We just solve the t first. It's not very difficult. You can cancel the pi first. Then divide by move this term to this side. You find the t is just 4 over 2m plus 1. Okay? This 2 times this 2 is just 4, so we divide by 4 here. This 2m plus this 1, 2m, well, then times the lambda oil. Okay? So that's the formula for the thickness of the oil. So right now we just write down for the 2 lights, 2 different wavelengths. For the red lights, 650 nanometer. So we get the condition is just 1 over 4, 2m plus 1 times the wavelengths of the red lights in the oil. We're talking about the wavelengths of the lights in the materials. It's just the wavelengths of that lights in the air or vacuum divided by index of that materials. So this time we need to use that number divided by the index of the oil. 650 nanometer, that's the wavelength in the air, divided by the index of oil, 1.5. Okay? Remember, this wavelength should be the wavelengths of light in the oil. Okay, so this one, if you plug in the number of m, because it didn't tell you how many times of the phase difference. So m can be any number. We just plug in any number. First plug in 0. If m is 0, that means that phase difference, total difference is just 2 times. Just 0. Just 0. In that case, you can calculate that number is 1/8 nanometers. If m is 1, it's also possible. So again, that number is 325 nanometers. If m is 2, can be also calculate. Any number is also possible. 5.2 nanometers, and so on. Then similarly for the second wavelength, 720, 390 nanometers. Still this formula, but the wavelength should be the violet in the air, 390 nanometer, divided by the index of the oil, 1.5. So again, you plug into 0, you will get 65 nanometer. You plug in 1, you will get 195 nanometer. You plug in 2, you will get 325 nanometer. If you plug to 3, you will get 465 nanometer. So look at later overlap. Hey. So that's the possible statement.